This video will explain one of the equations on the equation sheet and lead to the idea of resistivity, which is a topic that's only in AP Physics and not part of freshman physics. This is the general idea. What factors affect the resistance of an object? So imagine you have a cylinder here. It could be made of anything. It could be made of copper. It could be made of carbon, like the lead in a pencil. We put a voltage across it with a battery and we can measure a current through it. And this is the definition of its resistance. So now imagine we can change anything we want about this. Imagine you have the power to change anything about this cylinder. What could you change? What are the different things you could change to make its resistance bigger? So think about all the different things you could change to make the resistance of this bigger. And before we get into the theory, let's remind ourselves what these symbols mean. Delta V is change in potential. That's the loss of electric energy per charge. That's what that means. How much energy each charge that goes through loses. It's kind of like if you look at each car going down a highway, how much gasoline each car would use as it goes through some kind of, say, a tunnel or a road. And then I, of course, is the current, and that means how many charges go through this per second. All right, let's look a little bit at the theory. Now, you should pause the video and think. What are all the different things I could change about this that would make the resistance bigger? One at a time, go through them to try to figure out what resistance depends on. What actual things about that object could you change? All right, so let's look at the theory. Why do charges lose electric energy in the first place? Well, they lose it from colliding with the atoms or material in the resistor itself. That's our model. We don't have to go into any deeper science than that. Imagine what's blue, the blue squares. That's the atoms in the material in the resistor itself, and the electrons are moving to the right because a battery has set up a positive end and a negative end. So there's an electric field pointing this way through this object. And so the electrons, the free electrons that are current, that count as current, are drifting to the right. And as they move, they collide. They may start to increase in speed and then they hit something and they slow down. They lose energy. Then they start to increase and then they hit something and they slow down. But in general, they drift towards the right under the influence of the electric field created by the battery. So that's why there's the loss of energy that comes from collisions. Right? So that's written here. What happens to the actual atoms themselves in the resistor? Well, since they're getting smashed into, they start vibrating in place. They can't move out of their place, but they're vibrating in place more and more, and so they get hotter. And that thermal energy is then radiated out into the room or into the device, say into a personal computer, and it makes that device warmer. So how can we change the resistance of this object with all of this theory in mind? You could pause the video and think about it now, but we'll go through them. 3 different things we could change. The first is we could change the length. We could change it from the short length L1 to a longer length L2. And what that does, it's like making something with friction longer. It's like taking the hard part of a road. Say you have a road that is very difficult to travel on because it's very, very bumpy, and you're making that part of the road longer. Okay? So each electron has more collisions since it's going through more material, so it loses more electrical energy per charge. So that goes up for the same current. If you run the same current through it, you get a bigger loss of electrical energy per charge. So that means we've increased the resistance by making this longer. This is also like taking an original resistor and making it longer is like adding a resistor in series. It makes the total resistance bigger. Right? So if you thought of that, you can see what would come next. We could make it longer or we could make it wider. These are the 2 ways we could change the dimension of this cylindrical resistor that we have. So the second thing is we can change the cross-sectional area. And that's like making a pipe wider or making a road wider. Still the same length. So it's still the case, same length, still the same length. So each individual car is still losing the same amount of energy, or each individual car would be losing the same amount of gasoline to travel from here to here. So the gas per car is staying the same. That's the electrical energy per charge is staying the same. So the voltage would be the same, but look what we've done by making it wider. We've enabled it to carry twice as many charges. So it's like a wider pipe or road. You get the same energy loss per charge, but there are more charges going through per second because it's wider. They're not going faster, they're just more of them, because the object is wider now and can carry more. more per second, so it's got a bigger current, so the new resistance is smaller. So if you make the resistor wider, you get a smaller resistance overall. This is like having an original resistor like that and adding a second one in parallel. And that makes a total resistance that's smaller. If we double the area, it's like adding a second identical resistor. The resistance would be cut in half. Then the last thing we do, I hope you guessed this, was we could change the material. And here's an example. These are real numbers. If you have identical dimensions of copper and carbon, you can set it up so the carbon, and if you measure the resistance, then you'll find that the carbon has a resistance of 1.7 ohms, but the exact same shape of carbon will have a resistance of 3,000 ohms. Carbon is a true metal. Carbon is in that boundary area between metals and nonmetals, and it does not act like a true metal, but it's also not what we would call an insulator. So you can see a drastic difference when you change the material. All right, let's put all of this into one equation, the equation that's on your equation sheet for AP Physics. So if we make the resistor longer, the resistance should get bigger, but if we make the area bigger, the resistance should get smaller. So it's going to have a fraction. Pause and figure out what letter goes on top and which on the bottom. The L should be on top and the A should be on the bottom. So it's inversely proportional to the area and proportional to the length. And then finally, the material should matter, and it works out to be a fairly simple model that you can multiply by some number that's different for different materials. And we'll put a number sign here. You've seen this idea before. A number that's different for different materials. Be small for copper, big for carbon. Different for different materials. That number that goes there, of course, is going to have a name and a symbol and a unit. The name for it is resistivity. Not resistance, but resistivity. And you want to be very careful not to confuse the two. Resistance is what you learned in 9th grade and you've been doing so far. You're very comfortable with that. V equals IR, that's resistance. This is resistivity. It's a specific number that you multiply times the length, divide by the area, and you get the resistance of an object. The symbol for it is this. Now, you're not going to like this because you've seen that symbol before. Technically, I think you really don't put a tail on it. You write it like that. You've seen that symbol before. That's a Greek rho. And it's a lowercase r, even though it looks like a p. And we've seen it for what already? We've seen it for density. So this is a very unfortunate coincidence. The same symbol is used for both. But here it makes more sense. It's the rho, r sound for resistivity. Latinate r for resistance. Greek lowercase rho, which is their r, for resistivity. Those are two different things. Okay, here's an example that shows you the unit for it. Copper, this low resistivity, and the unit is an ohm times a meter. And if you put that in here, you'll see that that works out, and that gives you ohms, ohm meters. All right, whenever you have this, some number that's different for different materials, what is always in your book? A table. And we saw this before when we had mu in the first semester, mu k and mu s, right? The coefficient of static friction or the coefficient of kinetic friction here, different for different combinations of materials, so there would be a table in your book that can be used to do problems or to calculate, to identify things, right? Same thing here. There will be a table in your book of resistivities, and you can use that to solve the homework problems. Now, we'll pause and take a minute to explain what this means. But first, look at the equation now with the correct symbols in it. This is the equation on the equation sheet. You should be familiar with what each letter means for this. And now let's come back to this. Resistivity is what you call an intrinsic quantity. That means it's a property of the material, not the dimensions of the object. Other intrinsic quantities would be like color. This board is a white board. It's white. If I cut it in half, the color is still white. That doesn't change when I change the dimensions of the object. That's an intrinsic quantity. Another intrinsic quantity is density. It's one of the reasons we use it. Another intrinsic quantity is atomic mass, for example. That's an intrinsic quantity. So they're intrinsic quantities. They don't change if you change the dimensions of the object. They don't change if you cut the object in half. They don't depend on the size of the object. There are other types of quantities called extrinsic quantities, and think of what that would mean and what would be some examples of those. An extrinsic quantity does depend on the size of the object. So an example would be volume. If you cut an object in half, the volume would get smaller. That's an extrinsic quantity. So is total mass, an extrinsic quantity. So is resistance. Resistance is an extrinsic quantity. If we make a resistor longer, its resistance changes. If we change the dimensions of the object, the resistance changes. So resistance is an extrinsic quantity. It depends on the size. So which of these two types of quantities, intrinsic or extrinsic, which of the two would you use if you were a crime scene investigator or a forensic scientist to identify something? You want to identify whether something is blood or see what kind of metal it is. Would you use intrinsic quantities or extrinsic quantities? Well, of course, you'd use intrinsic because they don't depend on how much you have. These intrinsic are the ones that you can put in a table to identify what something is. Its density, its resistivity, its pH, that sort of thing. Although I'm not a chemistry teacher, I take that one back. pH within a certain solution concentration. So intrinsic quantities are used to identify things. And there's a little bit of a trend in science. They can't make it absolutely consistent. It's too late. But the trend is to use ITY for quantities that are intrinsic. So resistivity, density, conductivity. Those are three quantities that are all intrinsic. And in electrical engineering, at least, for extrinsic quantities, to use ANTs, if possible. Resistance, capacitance, conductance. Those are extrinsic quantities, whereas conductivity and resistivity are intrinsic quantities.